Okay, so looking at the thermodynamic cycle behind the heat engine process here. So we start out with the tank in the cold water. So we start out at the initial volume and the initial pressure. So after you put it in the cold tank and you open the valve on the piston to let it go to atmospheric pressure, and then you close it. So it starts at atmospheric pressure. And then once it's all the way cooled down, you put it in the hot tank. So the temperature is going to increase, and so pressure and volume are proportional to temperature. So those are also going to increase. Here I'll talk about how they increase. So the free body diagram of the piston within the tube. So there's the pressure inside the tube. It's pushing it up. So that force is the pressure times the area, and the area is on the side of the tube. You can get it from there. And then pushing down, there's the weight of the piston. And then also in this part of the cycle, you'll be pushing up something to drive your mechanism. So I'll call that like big M. So it's the big M, which is like whatever's on top of the stand outside of the piston plus a little m times gravity. And then, so it's a combined mass. And then there's also just atmospheric pressure times area pushing down too. So the volume is not going to increase, so the piston won't move up until the piston can move. So the piston is not going to be able to move until the pressure inside reaches like a threshold pressure for it to move up. So the pressure is just going to increase, the volume is going to stay constant until it reaches this P2. So once it reaches P2, then the volume will increase until it either hits the top or until the ideal gas law balances and the temperature and it reaches the highest temperature. So then this is at V2. And so this phase we can approximate as a straight line, but really there'll be a brief acceleration and deceleration period, or something like this. It's a little plateau. We can just approximate it as a straight line. So then for it to come back down, because it's going to be a box, so in your mechanism, there'll be this force here will be less because it will have pushed something up. So it'll be coming down, it'll be freer. So then it'll immediately, the piston, there'll be more forces pushing it down. So it's going to move down until you reach a new threshold pressure, which is usually going to be pretty close if your mechanism is designed well to the initial pressure, and then it'll just come back straight across. The volume will decrease. So then there you have the box of the cycle. And so the work is just P2 minus P naught times V2 minus V1. So we try to optimize the work with respect to the mass that you put on top of it. So we got something that looked like this, and this was around 1.4 kilograms, around 3 kilograms. It stopped being able to push it, and then this gave us around 3 joules. So those were with our numbers for V1 and the smaller mass and the area we calculated.
The piston provided to us is connected to a lever mechanism. As the piston goes up, one of the claws is pushed down one notch of the strip, and as it goes down, the other claw is pushed down one notch. As this lever mechanism is stationary, it results in the strip moving up. The predicted performance at optimal load of 1.4 was 3.01 joules per cycle. Multiplying this by the number of cycles we could fit into the 5-minute time slot, we could find the total potential energy stored.
performance, essentially we ended up going with a different mass of 0.12 kilograms, and our height, our change in height, ended up being 5.3 inches with our design. And so we calculated potential energy and then divided it by the number of cycles in our video, which is 5, and we came up with a work of 0.0317 joules per cycle, which is about 100 times less than our predicted value. And so some areas of improvement potentially in our design could be that in using MDF, we had a lot of friction between all the arms. So as the ratchet mechanism moved up, oftentimes it would get stuck, and there you would lose a lot of work, energy. And also, this whole mechanism has to be in one plane essentially, and a lot of times the screws were not perfectly sized to keep that way. And then the biggest issue was definitely that our piston was not sealed, which Joe will talk more about.
When setting up your piston, make sure that the screw is completely screwed out, because that screw just provides friction when it moves up and down. That's not what you want. And then also with the valves here, always keep this valve completely open, how it is shown here. And then the other valve at the start, after you've put the tank in the cold bath and left it in long enough for the temperature to go to the temperature of the cold bath, then you tighten this valve to seal the system.
Wouldn't that make like the